26.210 Circuit Breakers and Fuses, Section 2.0.0, Sizing and Selecting Circuit Breakers. Identify and describe circuit breakers and their characteristics, identify circuit breaker components, describe various circuit breaker types and their applications. And then, of course, your instructor is probably going to want you to be able to take a circuit breaker and tell them the number of poles, the loaded rating, the voltage rating, and the amperage interrupting rating. Circuit breaker is a device used for opening and closing a circuit manually or automatically in the case of an overcurrent event. Beyond the components that automate it, it's simply a switch with one or more sets of contacts. Switching can be done manually by switching the handle to the on or off position. However, a circuit breaker is also designed to open a circuit automatically at a predetermined overload or fault current value without damage to itself. As long as the circuit breaker is applied within its rating, it will automatically interrupt a fault and is formally classified as an inherently safe overcurrent protective device. Circuit breaker components. The internal arrangement of a circuit breaker is shown in Figure 2. The thermal circuit breaker contains a spring-loaded bimetal element that opens the circuit breaker contacts when excessive current overheats the element. The magnetic circuit breaker uses a magnetic field induced by current flow through a coil of wire to open the contacts and break the circuit. So a lot of times you'll have a dual circuit breaker. It's thermal magnetic. So it has an element that's magnetic. So if you have an over current impressed on this coil of wire, it will open the circuit contacts, or if the heat rises too much. So if you're using thermal, you have to kind of consider if the room the panel's in is hot. If you wouldn't want to put overcurrent protection devices, you wouldn't want to put a thermal element circuit breaker in a boiler room. Temperature rises, you could trip that circuit breaker just because of the ambient temperature in the room. So you would only put magnetic, and you try to locate those circuit breaker panel outside of the boiler room. You wouldn't put it in the boiler room. So here's the thermal element, and that is with temperature. If the temperature rises too high, including ambient air temperature and the temperature of the wire because of the current passing through it, it'll trip. And some of these thermal element circuit breakers have an adjustable, have a little dial on the face of them. And you can increase or decrease the amount of fault current just because of that, just to take into consideration the ambient air temperature. If it's in a room that's normally 100 degrees Fahrenheit, you would want to adjust that in order to take that into consideration. So you could get the actual current flow through that thermal element without it tripping. All right. Upon sensing an overload, the circuit breaker opens its contacts or trips. The piece of equipment that functions to signal the reset the circuit breaker when tripped is called the switching arm or the handle. And this is a highlight. The various positions of the switching arm are shown in Figure 3. So you can turn it on, you can turn it off. You can turn it on, you can turn it off. If it turns off automatically, meaning it tripped, the handle is going to end up in the center. So when you see the center of the circuit breaker in the center, you know that that circuit breaker has tripped for some reason, and you should investigate as to why it tripped. Too often, we in the field or at home will just reset this circuit breaker. You have to reset it by turning it past the off position, and you'll feel the contacts close. You'll feel a spring resistance against you, and you pull this handle down, and it'll click, and it'll reset that circuit breaker, and then it'll rest in the off position. Then you can push it forward to the on position, and you should have continuity through that circuit breaker. It should be, once again, operating correctly. If you try to reset a circuit breaker and it immediately goes back to center, that means there's a dead short somewhere. You've got to go investigate and find out what's going on. Like I say, too often when we find a tripped circuit breaker, the first thing we do is just reset it and turn it on and see if it holds. If it doesn't, then we go and we investigate. This is when the circuit breaker trips. The handle jumps to the middle position and typically displays a red flag in a tiny window. To reset it, move the handle toward the off position and push it as far as it'll go beyond it. To restore power to the circuit, move the handle to the on position. A common circuit breaker type is the standard molded case circuit breaker. It usually contains the following components: set of contacts, a magnetic trip element, a thermal trip element, line and load terminals, busings used to electronically connect to the individual parts above, mechanical linkage to reposition the contacts, and a housing of insulating non-conductive material. That's the molded case. Circuit breaker handle manually opens and closes the contacts. It also uses, it's used to reset the automatic trip element. Some circuit breakers also contain a manually operated push to trip testing mechanism. Circuit breakers are classified into amperage grouping that match specific physical dimensions. These numbers commonly referred to as the frame size or frame classification. They always take the largest amperage circuit breaker in that class. So between 10 amps and 100 amps, those frame sizes are classified as a 100 amp frame size. 125 to 225 are classified as 225 amp frame size. 250 to 400 are classified as 400 amp, and up to 1,000 amp is classified as 1,000. 2,000 amp is classified as 2,000. So you'll want to know that. They will ask you that on the test probably. So be aware of these classifications: 100, 225, 400, 1,000. Circuit breaker types and ratings. The established voltage rating of a circuit breaker is based on its clearance between conductive surfaces. This refers to the distance separating internal contacts as well as the distance separating its conductive electrical components and a ground source. So you got to make sure that you're not going to have an arc going to ground. And that's what, if you're using a 250 volt overcurrent protection device in a 480 volt circuit, more than likely you're going to have some arcing, and you're probably going to ruin the circuit breaker, and you're not going to protect the circuit, and you might even start a fire. So you don't want to do that. So for alternating current, it's 120 volt, 120, 240. We have a 240 volt. It's good for up to 250 volts. Anything higher than that, you got to go to 600 volt. So you got a 250 volt rating and a 600 volt rating. Anything higher than 240, you need a 600 amp. 600 volt rating. Circuit breaker can be rated for either alternating current or direct current system applications, or both. Single pole circuit breakers rated at 120 240 volt AC or 125 250 volt DC can be used singly or in pairs or on 3-wire circuits having a neutral connected to the midpoint of the load. These circuit breakers can also be used in pairs on a 2-wire circuit connected to an ungrounded conductors of a 3-wire system. So like a water heater. If you've got 120, 240, you can use a 2-pole circuit breaker that's rated at 250 volts. And you can hook up your water heater. It doesn't have a neutral. You just bring 2 hots and a ground. Current rating, here's a highlight. It says the ampere rating of a circuit breaker is located on the handle of the device as shown in figure 4. So look at the handle. It'll have the ampere rating on the handle of the device. So this is a square D type. This is their new home line. They have the QO breakers, which are older breakers, and then they've got the newer home line that are compatible with different types like GE and Kraus-Hein and what have you. But I like the Square D home line. This has 10,000 amps of interrupting rating right there. 10 KA, 10,000 amps, 120, 240 volt AC. It says it's listed for aluminum or copper, ALCU. All right. And if you're using it, wow. All right. HACR type. That's the call out letters, HACR. So it's a 20 amp circuit breaker, and look, they have on and off clearly marked on the circuit breaker, on, off, and here's a 1 and a 0 for any people in the binary system. Generally, the circuit breaker current rating must be equal to or less than the load circuit conductor current carrying capacity. It's ampacity. Ampacity, I was told, is a word that is coined by the National Fire Protection Association, or I should say the National Electrical Code. They took two words, ampere and capacity, and they mashed them together and made a portmanteau. They made a new word, ampacity. It's the current rating capacity of a conductor. It's their ampacity. Most overcurrent protective devices are labeled with the following current ratings: normal, current rating, and interrupting rating. The interrupting rating is a lot higher. So circuit breakers are available in a wide variety of sizes and types. Here's one of those old QO style of square D breakers. I can tell just by looking at the way that it stabs onto the circuit. This one I can't tell what type it is, but it's either a GFCI or an arc fault. It looks older to me. It looks almost, well, it's not a Zinsco. It looks like a GE or a Cutler hammer or what have you. And it has a white pigtail, which is the neutral wire. And you take both the hot and the neutral to the circuit breaker. That way the circuit breaker can monitor how much current's flowing on the hot conductor and on the neutral conductor at the same time. And this goes back to the neutral bar. You plug this into the neutral bar. So here's a shunt trip module. Here's a 3-pole square D breaker. 60 degrees Celsius and 75 degrees Celsius rating. Some circuit breakers are suitable for use with both 60 degrees Celsius and 75 degrees Celsius rated conductors. Others can be used with only 75 degrees Celsius rated conductors. Be sure to check the rating of the circuit breaker selected. For example, to use the 75 degrees Celsius ampacity rated conductors of size number 1 and smaller, you must make sure to use a circuit breaker rated for 75 degrees Celsius. To comply with NEC section 110.14c, termination at the load end of the same circuit must also be rated for 75 degrees Celsius. All right. Interrupting capacity rating. The amperage interrupting capacity of a circuit breaker is the maximum short circuit current at which the breaker will safely interrupt the circuit. So that's the interrupting rating. It might be stated as AIC, might be stated as IC. They might even spell it out and say interrupting rating. So AIC is based on the rated voltage and power frequency. 110.9 states that equipment intended to interrupt current at fault levels must have an interrupting rating at least equal to the available fault current at the line terminals of the equipment and its nominal circuit voltage. So equipment intended to break current at other than fault levels must have an interrupting rating at nominal circuit voltage not less than the current that must be interrupted. These things that are intended to break currents at other than fault levels are switches, disconnects. They're not intended to open because of a fault current. They're not overcurrent protection. They're just intended to break current. So they have to be rated for the current at which they will be opening the circuit. These NEC statements simply mean that fuses and circuit breakers must have a rating high enough to withstand the highest current to which they can be exposed without suffering damage. This NEC section emphasizes the difference between clearing fault level currents and clearing potential operating currents. Protective devices such as fuses and circuit breakers are designed to clear fault current levels and therefore must have short circuit current interrupting rating that are sufficient for the fault level. Here's a note, this is a highlight. NEC section 240.83c requires that circuit breakers with a current interrupting rating other than 5,000 amps have the rating clearly shown on the circuit breaker. By definition, circuit breakers that have not been marked with an interrupting rating have a rating of only 5,000 amps. You cannot assume any higher. Now what are they saying here? What are we going into? people are familiar with normal current carrying amp rating of fuses and circuit breakers for a 20 amp overcurrent protected device. As the current approaches 20 amps, the device becomes hotter. If the current slightly exceeds 20 amps, the circuit breaker will open normally, or the fuse link in a cartridge fuse will melt after a given time with little, if any, arcing. If 40 amps of current is instantaneously applied to the circuit, the overcurrent protected device will open faster, but again, with very little arcing. However, if a fault current occurs that suddenly exposes the device to 5,000 amps, an internal explosion would occur. One simple indication of this explosion is demonstrated by the blackened window of a blown plug fuse. That's a highlight. Here's another highlight. Thus, selecting overcurrent protective devices with the proper interrupting capacity is extremely important. We do not want these things to become a grenade. We don't want them to explode. All right. Consider the following analogy using a damped stream. All right, for figure 5. I will say this. Fuses are remarkable. They really are. Think about it. They have a melting alloy. When you get higher than 20 amps, that fuse link will start to heat up and it will melt. It'll break apart. Below 20 amps, it has to offer very little resistance to the circuit. In other words, at below 20 amps, it cannot heat up to a point of having a resistance that will in any way interfere with the working capacity of the circuit itself. That's why I say they're remarkable. It's amazing to me that they are a conductor for all intents and purposes. They are a conductor until you reach their rating capacity. When you reach their rating capacity, now they start to function as a fuse, and they will melt. They have a melting alloy fuse link that will melt and separate, and they also have something internally to extinguish the arc. As soon as that fuse melts, it's surrounded by sand or silica, some substance that's going to extinguish the arc. It's not going to allow it to continue to burn. Here's their river. Here's the dammed river. And then floodgates, overcurrent protection device, blah, blah, blah. I'm not going to go into it. All right. Read it. Ask your instructor about it. Inadequate interrupting rating results in the destruction of overcurrent protective device. See what happened here? The dam broke. Now there are dam pieces all in the river. All right, that's enough of that. Breaking the dam is a fault current release. Floodgates are destroyed because of inadequate interrupting rating. Short circuit current allows 50,000 gallons per minute to flow. All right, there's your screwdriver. That's the breaking of the dam. The dam broke, and the overcurrent protection device was not adequate. All right, I can't get into it. It's just me. I just can't wrap my brain around it. All right. NEC 110.10 states that the overcurrent protective device, the total impedance, the equipment short circuit current rating, and other circuit characteristics must be selected and coordinated to permit the device to clear a fault without extensive damage to circuit components. It's assumed that the fault will either be between two or more of the circuit conductors or between a circuit conductor and the equipment grounding conductor. The component short circuit rating is a current rating given to conductors, switches, circuit breakers, and other electrical components. If a fault current exceeds these ratings, it would result in extensive component damage. Short circuit damage can be the result of heat of the electromechanical force of a high intensity magnetic field. Rating is expressed in terms of time intervals and or over current value. I saw a picture of a panel once that was subjected to high fault currents, and the panel looked like a giant had grabbed it and just crushed it. The sides of the panel were pulled in like a science experiment. And the caption of the picture said that it was the strong magnetic field caused by the short circuit current that pulled the sides of the cannon. There was supposed to be cross bracing in the panel. There were no cross braces. Someone had removed them, and this thing crushed, like I say, like a giant just crushed it with his hand. All right. The intent of the National Electrical Code is to ensure that short circuit currents cannot exceed the short circuit current rating of the system components. Overcurrent protective devices must be used. They limit the current flow to levels within the withstand ratings of the system components. In most large commercial and industrial installations, it's necessary to calculate the available short circuit current at various points in a system to determine whether the equipment meets the requirements of NEC section 110.9 and 110.10. There are several methods. I think they use the point-to-point method. Let's hope that they don't get into the math here. All right. Let's see here. Previously, the UL tests were limited to a maximum of 10,000 amps, so the emphasis was placed on the NEMA tests with higher ratings. Now, since the UL tests include the NEMA tests as well as other ratings, an emphasis is placed on the UL tests. I'm going to highlight that. Know that the UL tests now include the NEMA test limits, which are higher than the 10,000 amps UL used to be limited to. All right. UL requires that molded case circuit breakers open within a certain time once an overcurrent event begins. For example, UL requires that a 240-volt molded case circuit breaker trips at 300% of its rated continuous current within 50 seconds. There you go. A breaker rated at 600 volts is required to trip within 70 seconds at 300% of its rated current. Currents between 7 and 15 times the rated current, depending on the voltage rating and frame size, are handled as overcurrent events by the thermal trip element. Currents above this level activate the magnetic trip element, so they trip almost instantaneously. Three main categories of interrupting capacity are the standard interrupting capacity, high interrupting capacity, and current limiting. Standard interrupting capacity circuit breakers. In residential applications, the available fault current is rarely higher than 10,000 amps. In most cases, the available fault current is far lower. Like I say, you can buy 5,000 amp interrupting rating circuit breakers at Home Depot. Maybe nowadays, I haven't checked in quite a while, maybe nowadays they're all rated at 10,000 amps of interrupting rating, I don't know. High interrupting capacity circuit breakers. If a circuit breaker requires higher interrupting capacity than the standard rating, the FH, H stands for high interrupting capacity, is available. FH type circuit breakers has an interrupting rating of 65,000 amps, symmetrical at 240 volts AC. The continuous current rating at the same are the same as the standard versions, but the interrupting capacity has been increased to satisfy the need. So it's a different frame size. These are commercial and industrial. These are big circuit breakers. You wouldn't put these in your home. So you don't have to worry about the interrupting rating at your house. But there's your H for the high interrupting rating. 65,000 amps. And again, they do have fine adjustments of these to change slightly for ambient temperature. Current limiting circuit breakers. The need for current limitation is the result of increasingly high available fault currents associated with growth and interconnection of modern power systems. Current limiting circuit breakers have been developed to meet this need. The type of circuit breaker responds extremely fast to provide downstream protection for other types of overcurrent protective devices with as little as 10,000 amps interrupting capacity on systems with 100,000 amps available fault current. So a current limiting circuit breaker is basically a conventional thermomagnetic circuit breaker with an independent limiter section in series with each pole. For purposes of explanation, each limiter can be represented by a set of contacts shunted by a transformable resistor. At currents below roughly 1,000 amps, the current limiting circuit breaker performs like a conventional thermomagnetic circuit breaker. That's a highlight. For 100 amp frame current limiting circuit breakers, the threshold of current limitation occurs between 1,000 and 2,000 amps. Above this point, the limiter contacts open first, initiating the limiting action within 0.25 milliseconds. A substantial arc voltage is generated across the limiter contacts. The rapid generation of this arc voltage is essential to drastically limit the peak current allowed to pass through the fault circuit. So 0.25 milliseconds. One cycle of AC at 60 hertz is about 16.7 milliseconds. So you can see this is limiting far quicker than one half cycle. Half cycle is about 8 milliseconds. This is reacting in 1/4 of a millisecond. All right. What does it say here? Rapidly rising equivalent resistance of the arc across the limiter contacts forces the current to transfer to the alternate path provided by the limiter resistor. This special resistor has a high positive temperature coefficient. As the fault current is transferred to it, the temperature of the resistor increases rapidly with a consequent rapid rise in its resistance. I don't think they're telling us anything we really need to know, so I'm just going to go on. All right, let's go to the next page here. Series rated systems. NEC sections 110.22 and 240.86a require special markings for UL recognized series rated systems. For example, NEC section 110.22b states that equipment enclosures for circuit breakers or fuses must be legibly marked in the field as directed by the supervising engineer when applied in compliance with the series combination rating. The ratings are determined with engineering supervision in accordance with section 240.86a. The directed markings indicate the equipment has been applied with a series combination rating. The marking must easily be visible and read as shown, read as shown in section 110.22 to include the current rating of the system. So let's see if they'll show us. Oh, well, here are a couple. Most overcurrent protective devices are labeled with 2 current ratings. So again, if your circuit breakers are not listed, they're 5,000 amps of interrupting rating, and fuses start at 10,000 amps of interrupting rating. This one says it has 200,000 amps. Series rated circuit breakers. Let's see what they tell us here. Now, the NEC recognizes series rated circuit breakers as required and requires that the end use equipment be marked with a series combination rating. Such a series rating of devices is specific to individual manufacturers. For this reason, it's especially important to consult listing information or product literature for details of how a certain combination rating was derived. I'm trying to find the picture. I thought they had a picture in here of a series rated panel and a non-series rated panel. Non-series means each circuit breaker has to have an interrupting rating equal to the maximum fault current available at the line side of the panel. Series rated says that the further you get away from the main disconnecting means, the lower the interrupting rating has to be. You can take into consideration all of the values of interrupting rating along the way. That's why it's series rated. So you can have a main circuit breaker that has 100,000 amps of interrupting rating, and your branch circuits can have a rating of 10,000 amps. They can be less than the main circuit breaker. All right. Let's see here. Ground fault circuit interrupters. Fault current protection is extremely important to anyone who uses power tools and similar equipment. Remember that a fault current exists when an unintended path is established between an ungrounded conductor and ground. This situation can occur not only in worn or defective electrical equipment, but also when accidentally misusing equipment that is otherwise in good working order. So the hand-to-hand body resistance of an adult lies between 1,000 ohms and 4,000 ohms, depending on moisture, muscular structure, and voltage. The average value is 2,100 ohms at 240 volts AC, and 2,000 ohms at 120 volts AC. Using Ohm's law, the current resulting from these average hand-to-hand resistance values is 120 milliamps. So here they're showing us around 5 milliamps, you get a generally painful shock. Around 15 milliamps is sufficient to cause freezing, unable to break contact. That's the uh, let go threshold to the circuit of 50% of the population. So that's the let go threshold. Around 30 milliamps, breathing becomes difficult, possible suffocation. 50 milliamps to 100 milliamps is possible ventricular fibrillation or very rapid uncoordinated contractions of the heart ventricles, resulting in loss of synchronization between the heartbeat and the pulse beat. Once ventricular fibrillation starts, it usually continues and results in death within a few minutes unless special defibrillation equipment is used. 100 milliamps to 200 milliamps, certain ventricular fibrillation. That's why you need a defibrillator. And over 200 milliamps, severe burns and muscle contractions. The heart is more likely to stop than to fibrillate. All right. I'm not going to read the case history. A conventional overcurrent device will not open a circuit to prevent bodily harm. Current that would flow from a defective electric drill through the metal housing in the human body to ground would be about 60 milliamps, calculated using the above value of 120 volts AC. The 60 milliamp current is less than 0.5% of the rating of the 15 amp circuit breaker or fuse, and yet it approaches the current level that can initiate ventricular fibrillation. Obviously, the standard circuit breaker or fuse will not trip or blow, providing no protection for the worker using the drill. Ground fault circuit interrupters are Class A protective devices built in accordance with UL Standard 943. UL defines a Class A device as one that will trip when a fault current to ground is 6 milliamps or more, but it must not trip below 4 milliamps. They used to say 5 milliamps plus or minus 1 milliamp. So 4 to 6. There are two types of GFCI receptacles. The feed-through type will provide GFCI protection to the remainder of the outlets in the circuit, similar to a GFCI circuit breaker. The non-feed-through type offers protection only at the point of installation. Class A GFCIs provide a self-contained means of testing its operation as required by UL. To test, simply push the test button and the device will respond with a trip indication. And then you can reset it. OSHA and other codes require the use of GFCIs on certain circuits, including all construction sites where temporary services is provided for electric power. So residential and commercial garages, residential, commercial, and industrial bathrooms, all kitchen countertops, receptacles, and any receptacles mounted within 6 feet of a sink, residential crawl spaces and unfinished basements, outdoor public spaces, bathhouses, building rooftops, and dock sides. I believe you find that in 210.8 of the code. In addition, GFCI protection is required for the following circuits. Circuits for electric pool covers, power and lighting circuits for swimming pools, fountains, and similar applications, and branch circuits derived from auto transformers. So you're getting the idea. It's anywhere where you have moisture, anything wet. So in the kitchen, in the garage, in basements, in crawl spaces, anywhere wet, outdoors. When installed properly, GFCI circuit breakers continuously monitor the current in the two conductor wires of the circuit, both the grounded and the ungrounded conductor. The current in these two conductors should always be equal. If the GFCI senses a difference of more than 6 milliamps in current flow, it assumes that the difference is due to fault current and automatically opens the circuit. All right. So there you go. So this goes to the panel neutral. Usually there's a pigtail here. I guess they're giving us a screw, and you can tighten that screw. Panel neutral terminal. This goes to the panel neutral. Here's the neutral from the device that you're protecting. It goes in, and then wherever there should be another screw. Oh, I guess this is just the strip gauge. No, I'm not sure. But you'll have 3 screws here. One for the hot, one for the neutral, and then a third for the panel neutral that goes back to the neutral board. All right. Other types of circuit breakers. Apart from circuit breakers that protect against overloads and overcurrent events, some circuit breakers have additional capabilities or functions. The following are some examples of these circuit breakers. Shunt trip circuit breaker. This circuit breaker adds an internal electric coil that causes it to open the circuit breaker contacts when the coil is energized by an external source. So you might have an emergency button that you can push, and it will trip that shunt trip circuit breaker. For arc fault circuit breakers, this type of breaker includes electronic circuits to monitor current flow within the circuit breaker. If it detects a pattern of small continuous surges or spikes in the current flow, the breaker will open. So it will, in essence, prevent a fire in your house because of arcing. GFCI circuit breakers. The GFCI breaker includes circuitry to monitor current in both the conductors of the circuit. If there's an imbalance of those currents of more than 6 milliamps or more, the circuit breaker will open the circuit, and as described previously. And switch neutral circuit breakers. This breaker disconnects the neutral or grounded conductor simultaneously with all ungrounded conductors. Breakers that switch grounded conductors are used in installations such as fuel dispensing equipment. Non-automatic breakers. A non-automatic circuit breaker has no devices to protect the circuit against overcurrent events. It's used as a means of manually disconnecting circuits by operating the handle, similar to a non-fused disconnect switch. It's also known as a molded case switch. All right. The code used to limit us to 42 circuit breakers in a panel. They no longer say the number 42. Now they say as per manufacturer's installation requirements. So you have to check with the manufacturer to see how many circuits that panel is actually good for. But I think that the manufacturers still do limit it to 42 circuits per panel because of cooling. You want to be able to dissipate the heat caused by all of these wires and all the current flowing in those wires. So this one has an extremely large trough, so it could probably dissipate more heat. You have more room than a regular home panel. They're more narrow, and there's not enough room for wires to dissipate their heat, so they used to limit it to 42 circuits. Here's section 2 review. 250 amp fuse has a frame size of what? We have to go back and look. And at 300% of its rated current, a circuit breaker rated at 600 volts must trip within how many seconds?